Hello everyone and welcome to another Stat 437 lecture video. In today's lecture we're going to be talking about marginal linear models more, and in particular we're going to be discussing the theoretical considerations for these models. So we're going to be looking at the likelihood derivations, the asymptotic distributions, sort of the details of everything that we covered in the last lecture where we introduced these models. So hopefully this video serves as both informative about the underlying theory and also as a way to help you review those concepts that we talked about there. As always, if anything's unclear, please let me know and I'm happy to answer any questions that you might have. But for now, I will open up the whiteboard here and we can sort of begin. So the first thing that I want to talk about is the likelihood derivation. So if you remember, the idea with these marginal models, these linear marginal models, is that we wanted to extend linear regression to this place of a multivariate normal distribution. So we had yi being our outcome variable, and this is going to be a vector for each individual where the vector contains all of the components, so yi1, yi2, and we'll say y up to yik for each individual, right? So these are all of the longitudinal observations that we had. And what we said was that if we assume that yi is distributed as a multivariate normal distribution, where the mean is given by xi beta, and the variance is given by this sigma I matrix, then we can use that assumption to estimate this beta parameter much in the same way that we did for linear regression, right? And we can do this through a maximum likelihood estimation procedure. So to clarify, in case you haven't seen it, in case you don't remember seeing it, if we have a multivariate normal, we can write out the density of that function. So say the density f of yi, and I'm going to parameterize it using this mu here and a sigma, right? And so in our case, the mu is going to be equal to xi beta, and sigma is equal to sigma I, but for now I'll use sort of this more standard notation here. And the density is going to be given by the determinant of 2 pi sigma to the power of -1/2. And then from there, we multiply that by the exponential, and the exponential takes in this quadratic form, which is going to be -1/2 yi minus mu transposed sigma inverse yi minus mu. Okay, and so get that all visible for you there. So this takes a similar form to the distribution of a normal density, where the difference is that because yi is a vector, we have this quadratic form here, so we're taking the inverse matrix and we're using transpose times by the regular term as a way of sort of representing the square that would normally be up there. And also this term out front, instead of it being the square root of the square, we're looking at the square root of the determinant, right? But otherwise it should look fairly familiar. And then the basic idea is that if we replace mu here with xi beta, and we replace sigma with sigma I, then we can find the MLE, and that will give us that estimator that we saw in the previous lecture. And so in order to do this, what I want to actually do is just focus, instead of on the full likelihood, I want to focus right on the score function, because that's going to be a little bit simpler to work with. But to remind you all, if we want to take the likelihood of some parameter, so likelihood of, say, beta and sigma I, this is going to be equal to the product over the whole sample, so I equals 1 to n, of f of yi, where f is the density function here. And then normally we would take the log likelihood, so that's going to be the log likelihood of beta and sigma I, which we get by taking the log of this expression. And when you take the log of a product, it becomes a sum, and so that becomes the sum by equals 1 to n of the log of f of yi, right? So if we want to then write out the score function, in general, we would say that the score function of some parameters is given by the derivative or the partial derivative of the log likelihood function, right? But so in particular, if we're just assuming that we have one observation, and let's say that we're only interested in the parameter beta for right now, then what we can do is we can say that the score function of beta is going to be equal to the partial derivative with respect to beta of the log of this density function here. And the reason that we care about this score function is because if we solve s of beta hat equal to 0, right, if we set that and solve for what beta hat has to be, then that's going to give us the maximum likelihood estimator, assuming that regularity conditions are met and such, but we'll just assume that, that those are. Right, so the idea here is then we want to work with this expression, and that's going to be how we derive this MLE, okay? So we can actually do that. We can write out what the log for an individual is, right? And so if we want to say the log of f of yi, right, that's going to be the log of the density that we had written up here, right? So it's the log of this. And so we can do the log of 2 pi sigma I now, because we've plugged in our values, -1/2. And then it's the exponential, -1/2. And then we have this quadratic form, right? So it's yi minus xi beta transpose sigma I inverse yi minus xi beta. Okay? And we are taking the log of that whole thing. All right, so now using some log rules here, we can see that there's this multiplication between the determinant term here and this exponential function. And so when you're taking the log of a product, you can sum over those logs, and then we can pull out, do some simplification from there. So this first term, right, it would be the log of the determinant raised to the power of -1/2. So you can pull the -1/2 out front, and then we have the log of this determinant. That's 2 pi sigma I. And then when you take the log of this exponential function, the log and the exponential cancel each other out, and we're left with -1/2. And then we have this quadratic form here. Right, so that's yi minus xi beta transposed sigma I inverse yi minus xi beta. Okay, and so from here, what we want to do is we actually want to get the score function by differentiating this. And we want to differentiate it with respect to beta. Now, if you're not super comfortable with multivariate calculus, I don't blame you. It's been quite a while since I took a multivariate calculus course. There is one resource that I would highly suggest that you check out. And so if I open this up over here, I have the Matrix Cookbook open. So if you just Google for Matrix Cookbook, there's this PDF file that is sort of a great resource for working with matrices, especially with calculus related to matrices. So you can see in the table of contents, they have all sorts of things, but the chapter that I continually come back to is chapter number 2, which does derivatives of matrices and vectors. And so if we just open up chapter 2 here, you can see that it's just a book with loads of results about different differentials, different derivatives of traces, of determinants, of different forms of matrices with respect to vectors or scalars or anything else. And so when you're working with expressions like this, and this starts to come up a lot in multivariate statistics, broadly speaking, eventually you'll get more comfortable with working with these things, or you can, rely on that knowledge. But it's also a super useful resource to come in to check out and say, am I doing this right? Am I applying the rules of multivariate analysis, right? And I would highly recommend that you sort of have this bookmarked and you're comfortable coming back to it. Now, the reason that it's so useful for us right now is because we're going to be taking the derivative of this expression with respect to beta, right? And so we can take a look first and note that in this first term, there is no beta. So the derivative of that with respect to beta is going to be equal to 0, right? So that's easy enough. the second term here, right, we have beta in these second components within the brackets of this quadratic form. And so what I'm going to do actually is rewrite this slightly. If I factor out the negative from each of these brackets here, you can see that the full sign of the expression isn't going to change, but we could write this instead as negative 1/2 xi beta minus yi transpose sigma I inverse xi beta minus yi. Okay, and we can sort of ignore this constant term out front for a number of reasons, but for now, we're just going to focus on this second half of this component. And if you take a look at 78 over here, right, you can see that what we're doing is we're taking the partial derivative with respect to x. X here is a vector, and they do define all of their notation at the start of the chapter, so you can take a peek at that. But if you see, we're taking the derivative of an expression of this form, bx plus b transpose c dx plus d. And so in this case, because we're differentiating with respect to this x here, the x is going to correspond to our beta, right? So if we take x equals beta, then you can see that our expression basically maps onto this, right? So we have this b, where in our expression, it's going to be equal to xi. And then we have, so bx plus b, in our case, the little b is then minus yi, right? And same thing in this other bracket, or the c term, I guess, next, would be sigma inverse for us. Sigma I inverse. And then we have dx plus d. And in this case, the brackets are exactly the same for us, right? And so this is going to be equal to d, this is equal to little d. And so we are actually working in this exact form here for number 78. And what that means is we can just read off what this derivative actually is. And so we know that the derivative is going to be b transpose c, and then times by the bracket. And so in our case, that's going to be xi transpose sigma I inverse. And then we take the bracket, so that's xi beta minus yi, right? And then plus this term here. And if you actually take a look, when we take d transpose c transpose bx plus b, we're going to be looking at exactly the same term again, because sigma I here is a covariance matrix, and covariance matrices are symmetric. And so we're actually going to end up with the derivative being 2 times this term. So if I went over that a little bit quickly, I apologize, but essentially all I'm doing is I'm, corresponding each of our terms with one of the terms in this expression, and I'm just copying down that expression. But what this means is that we know that the derivative of this log likelihood expression here is going to be equal to 0 for the first term, minus 1/2 times by this, but the minus 1/2 and the 2 are going to cancel each other out, right? And so we can write that as exactly xi transpose sigma I inverse, and then xi beta minus yi, right? And this is going to be our score function of beta, where we're looking at just a single observation. Now, more commonly, you're going to see this written as the negative xi transpose sigma I inverse yi minus xi beta, and that's just because that yi minus xi beta, that residual term, comes up quite frequently. But so now all we would have to do is actually solve this for beta hat, right? So we would have s of beta hat, and this is going to be equal to, we want to solve this equal to 0, sorry. And so if we actually just plug beta hat into this expression up above here, you could see that we would have negative xi transpose sigma I inverse yi minus xi beta hat. That's equal to 0, right? And so multiply through this matrix here, and then sort of rearrange the equation, we would end up with xi transpose sigma I inverse xi beta hat is equal to xi transpose sigma I inverse yi. And so if we treat this term out front here as one matrix itself, as an invertible matrix, and for some reasons it's typically going to be an invertible matrix, then we get beta hat equals xi transpose sigma I inverse xi invert the whole expression xi transpose sigma, that's a really bad sigma I inverse yi. Okay, and this is essentially the likelihood expression that we derived for beta in the previous lecture, where the only difference is that instead of doing it for one individual, we have the summations, and so then each of these brackets would have a summation in it. And I'd encourage you to walk through if you're actually using the log likelihood up here instead, right? And the derivative is going to be the same for each of those terms. And so then if you just do that last step of solving, you should get back to that expression that we saw. All right. Now, we could also do the exact same thing for the maximum likelihood with respect to the other terms that we saw in the previous lecture, right? So we saw that we decomposed our sigma I matrix when we assumed that there was constant variance into sigma squared times by Ri, and Ri took this parameter rho, right? And so we also wrote out maximum likelihood for rho and for sigma squared here, okay? And the process is going to be exactly the same. The math ends up being slightly more convoluted, but more or less the same process, and I'd encourage you to work through that yourselves. But what you'll find if you try to do this is that for sigma squared, we can actually come to a definitive conclusion. We can write out an explicit solution for it, but for Ri of rho, we can't. There's no way to explicitly solve for the rho parameter here. And so because of that, we're going to need to use some alternative methods to solve it. And so in general, what we're actually going to be doing is we're going to be writing down sort of what is called a profile likelihood equation. And the idea is that if you have estimated beta hat and sigma hat squared, right, then we can solve the likelihood, the log likelihood, say, of beta hat sigma hat squared rho, right? And we can solve this numerically for rho. So essentially what we're doing is we're saying we use our closed form estimators for beta hat, we use our closed form estimators for sigma hat squared, and then we take those as though they are the true values, the correct values, we plug them into the likelihood, and then we can solve using some numeric techniques for the rho parameter here. And this is a technique known as profile likelihood. The details of it aren't super important, but I would highly advise that you take a peek at sort of the derivation of the maximum likelihood for both of these terms here, for the sigma squared and the rho, and convince yourself that there isn't a closed form solution for this rho here. But otherwise, I hope that all of that made some sense. And once you have the maximum likelihood estimators, we can start to do some analysis using it. So the next point that I want to bring up is the idea of finite sample bias and using that to discuss something called restricted maximum likelihood estimation. So if you think about when we're using variance estimation, just standard variance estimation from a sample as you would have seen in all of your stat courses before, we always use sigma hat squared is equal to 1 over n minus 1, and then we take the summation of xi, say, minus x bar squared, right? This is our common estimator for the sample variance. And the reason that we use this 1 over n minus 1 term here instead of using 1 over n is because this 1 over n minus 1 removes bias in a finite sample, right? So this estimator up here is unbiased. If we had used 1 over n times by the sum I equals 1 to n xi minus x bar squared, this estimator right here is biased in the finite samples, right? And as n goes off to infinity, 1 over n minus 1 and 1 over n, both approach 0 at exactly the same rate. And so these two estimates become closer and closer in larger and larger samples. But this estimate using 1 over n is actually the maximum likelihood estimate if we're talking about normal distributions, say, right? And so the question is, why do we typically use this first estimator? And the answer is because it's unbiased. So we're going to actually run into a similar problem with the estimates for sigma hat and rho in the process that we've outlined here. If we use the maximum likelihood estimates of these parameters, we're going to run into finite sample bias. And this isn't going to be a problem if we have a sufficiently large sample, right? In a sufficiently large sample, we see that these two are going to be equivalent, essentially. Same thing in our process for these linear marginal models. But in smaller sample sizes, this actually can make a fairly large distinction. And so we can introduce a concept known as restricted maximum likelihood. So we'll just say restricted ML. And typically this is abbreviated to be REML. And the idea with restricted maximum likelihood is that we can actually solve the likelihood expression for one of our parameters and then modify our likelihood expression for other parameters that reduces this small sample bias. And so in particular, for our situation, we can write out, I'll call it L sub R for the restricted. And the idea is that we're going to use the exact process we just worked out to derive the maximum likelihood estimate for beta, and then we use a restricted maximum likelihood for sigma squared and rho. And the reason that we do this is because typically we don't actually care about these two parameters. Typically they're nuisance parameters. We're not really going to use them. We just need them to be able to perform inference, right? And we derive this restricted maximum likelihood equation here as the difference between this sort of profile likelihood expression that we just talked about. So you plug in beta hat, which has been estimated, and then you subtract off this penalty term here, which is going to be 1/2 the log of, and then if we're talking about a sample of size n, we would sum I equals 1 to n, xi transpose vi inverse. Remember that vi is our working covariance matrix. So in this case, we're thinking of vi as sigma squared ri rho, and then xi. And if we then take this as though it is a likelihood expression itself, we can solve it for the sigma hat squared and the rho hat, which maximize it. And the specific details of why this works, where this is coming from, none of that's actually particularly relevant for this course. If you want to ask me, I can sort of share one-on-one what we're doing with this. But the idea is that by using this sort of penalty term here, we're reducing the bias that is present in the same way that we reduce the bias with this 1 over n-1 term instead. Now, there's a few things that we have to be careful about. So the first is that when we're using restricted maximum likelihood, we change the asymptotic distribution that we're looking at, okay? And so we have to be a little bit careful about how our asymptotic analysis is going to come. And then the other point is that they're not true likelihood expressions, okay? And so if you remember from your GLM course, for instance, and if not, we'll be reviewing this briefly reviewing this momentarily in the next coming lecture. But in GLM, we use differences in the estimated likelihood to test for model fit, for instance. And so we're not going to be able to do that with a restricted maximum likelihood. But our basic process is going to be, we'll use maximum likelihood to estimate beta hat. We'll use restricted maximum likelihood to estimate sigma hat squared and rho hat. And then if we need to perform some type of inference that requires it, we'll either use sort of modified procedures, or we can fit the model using maximum likelihood to perform all of the inference we need. And then when we want unbiased or approximately unbiased estimators, we use the restricted maximum likelihood in those settings. Okay, so again, the specific details aren't super important. We'll see when we're implementing them in R that we can just specify restricted maximum likelihood as an option, and we can use that instead of maximum likelihood. But that is actually going to be the way that we end up estimating these parameters, generally speaking. So the next point that I want to discuss briefly is how we actually use this asymptotic distribution. Now, in the last lecture, I did walk through this sort of briefly, and so I'm going to do that again just to sort of get this idea across, right? But what we're saying is that when we've used the maximum likelihood estimate for beta, we know that beta hat is going to be approximately normally distributed, where its mean is the true mean, and then its variance is an expression that's included on the slides there. It's kind of a gross looking expression, but ultimately it can be estimated from the data. And so the idea here is that, well, this is actually a multivariate normal distribution, right? Because beta is going to, generally speaking, be a vector. But using this normality, we can start to test hypotheses about beta, we can build out confidence intervals, etc. And the key result that we're going to be looking at is that when we have this normality condition on beta hat, what we're also going to find is that if we take any component of it, so beta hat j, this is going to be approximately normally distributed with a mean of the true value beta j, and the variance is going to be, say, the variance of beta hat j, right? And if we think about the variance of beta hat, this is going to be a matrix, a p by p matrix. And if we take the jth entry, or so the jth entry along the diagonal, then that's going to be this term of the variance of beta hat j. And so because we know that beta hat j is approximately normally distributed, we can do all of the types of things we would normally do with an approximately normally distributed estimator. So in general, we're going to be able to do hypothesis testing. So if we want to test beta hat j equals beta star, for instance, well, under the null hypothesis where this is true, well, then we know that beta hat j is going to be approximately normally distributed with a mean of beta star and a variance beta hat j, where again, that's coming from that matrix, the jth diagonal of that matrix. And so that means that if we take, for instance, beta hat j minus beta star, and we divide that by the standard error of beta hat j, this should follow approximately a standard normal distribution. And so we can compare this value to z-scores to compute a p-value, for instance, and then test that hypothesis. Of course, this is exactly the same procedure as when we want to build out a confidence interval, right? So again, if we know that beta hat j is approximately normally distributed, well then if we take beta hat j plus or minus, and then we have some sort of z statistic here, times by the standard error of beta hat j, then this is going to be a walled type confidence interval for beta hat, right? And so z here is going to typically be, say, 1.96 to get a 95% confidence interval. But again, this is a process that you've seen very often. So that's generally how we're going to use the asymptotic distribution for beta hat. The other asymptotic distribution that we saw is the asymptotic distribution of, pull it up here, the asymptotic distribution of L beta hat, right? And so here, again, we did discuss this briefly in the last video, but to clarify this point here, so we're thinking of L as some matrix here. Generally, it's going to be a matrix that only has ones and zeros or negative ones in it, but it could be any matrix. And in particular, we're going to think of it as a matrix with rank R. Okay? And the idea is that because we know beta hat is normally distributed, any matrix linear combination of beta hat is also going to be normally distributed, right? So L beta hat also follows a normal distribution. And so if you have seen sort of a course that uses multivariate normals quite often, you may have seen how we can convert this into a nice chi-squared hypothesis test. So if not, if you remember that if we take z as standard normal, then z squared is going to be chi squared 1. Okay. Right, so this is a result that should remember from an intro stats course, for instance. A similar result happens if we're talking about multivariate normals, right? So if we think about, instead of taking Z to be standard normal, well, we have L beta follows this normal distribution with a mean of L beta and this variance of L variance of beta hat L. And so if we take L beta hat minus L beta, well, this is going to have sort of centered this value. So L beta hat minus L beta is going to be a normally distributed value with mean of 0. And so if we multiply this by the inverse of our variance here, so L var of beta hat, L transpose inverse, and if we then take the same term here again, L beta hat minus L beta, this quadratic expression here, so this quadratic form, right, we have essentially a standard normal times by a standard normal, so we're going to get some sort of chi-squared out of it, and in particular, we're going to get this to be a chi-squared distribution with rank R, or with degrees of freedom R, where R is the rank of L. Okay, so I don't know if you've seen this result before. If not, you can sort of take it on faith here that this is going to hold, but the reason that this is particularly useful is because we now can convert this into a single, a set of hypotheses into a single test statistic that we can then test the p-value of. So this allows us to test joint hypotheses all at once. So again, if you wanted to say, let's say that we had beta is equal to 3 terms here, beta 0, beta 1, beta 2. Now every hypothesis about beta can be expressed sort of as a set of hypotheses expressed in this matrix form. So let's say that we had a few different hypotheses that we wanted to test. Maybe we want to test if beta 0 equals 1. Maybe we want to test if beta 1 is equal to 2 times beta 2, right? Then the idea is that we can also see, or we can then see that these hypotheses can be expressed as this L matrix, right? So this first hypothesis, if we want to test just it alone, well then if we take L as equal to 1, 0, 0, then when we take L beta, this is just going to give us beta 0, right? And so then in this case, L beta equals 1 is a test of this hypothesis beta 0 equals 1. Okay, now if we want to test these jointly, then we also need a second row to test this second hypothesis here. And so how can we do this? Well, we can rewrite beta 1 equals 2 beta 2 to be the same thing as beta 1 minus 2 beta 2 equals 0. And now if we think about taking a row as 0, 1, negative 2, well, if L beta now equals 0, then we would know that beta 1 minus 2 beta 2 equals 0, as we've tested in this hypothesis. So putting those two together, if we take L to be this matrix, this 2-row matrix where we have 1, 0, 0, and then we have 0, 1, negative 2, now suddenly L beta can be thought of as testing our hypotheses, right? And so then we can plug this in, and we want to know under the null hypothesis, we would expect this to equal, L beta should equal 1, 0 under the null hypothesis. And so if we take L beta hat minus L beta and use this expression up here, then we can test that against a chi-squared 2 distribution because there are 2 rows here, the rank is 2. All right, so that's generally how we're going to use this. Of course, we can also use it for prediction, where if we take L to be a matrix of covariates that we are interested in, then we can sort of generate the prediction intervals that you might think of. Okay, so the last piece that I want to talk about today is the interpretation of the parameter estimates of beta hat. So recall that the model that we're actually fitting here is a model where we've specified that the expected value of yi given xi is equal to xi beta, right? And just as with a standard linear regression, oftentimes this is going to be easier to think about written out sort of more explicitly. So maybe that's going to be beta 0 plus beta 1, xi1 plus beta 2, xi2, etc. Right? And in actual fact, this is going to be yi here is going to be a vector, and these xi1s, xi2s are going to be vectors as well. And so this is actually a multivariate outcome, because for every time point we have a different time point. So to write this out somewhat more explicitly, we can take, say, a fairly simple example, and let's say that yi is just going to be two outcomes here. So we're going to have yi1, yi2, right? So we've just measured longitudinal data at 2 time points. And let's say that we take xi to be a fairly simple matrix where we're going to say have an intercept term. So the first column is going to be all ones. And then let's say we just have one or two factors that we care about. So we can say that this is going to be xi11, xi12, and then this is going to be xi21, xi22. Okay? And so now when we take beta, when we take the expected value of yi given xi equals xi beta, then beta here is going to be a 3-parameter value. And so we're going to have, I'm going to pull this onto a new page here, 1 sec. So we're going to have beta is equal to beta 0, beta 1, beta 2. And really, when we write out this expected value of yi given xi equals xi beta, what we're saying is that the expected value of yi1 given xi1 is going to be equal to beta 0 plus beta 1 xi11 plus beta 2 xi12, and then the expected value of yi2 given xi2 is beta 0 plus beta 1 xi21 plus beta 2 xi22, for instance, right? And so we can see that these parameters, these models, end up looking a whole lot like linear regression models, right? And in fact, our interpretations are all going to be based on the same linear regression interpretations that you are used to seeing. So we're working from an average here, a population average. And so the conclusions that we draw are going to be something like the coefficient represents the expected increase in our outcome when there's a unit change in the covariate, assuming that everything else stays constant. Okay, and so the if we think about what is beta 1 doing here, right, in this model? Well, beta 1, if you increase xi11 or xi21, if you increase these by 1, so you increase them by 1, then we see that the expected value of this outcome is also going to increase by beta 1, assuming that xi2 or xi12 stays exactly the same, right? So it's going to represent a unit increase in the expected outcome, assuming that the second covariate stays the same. Now, it might be helpful to make this somewhat more concrete. And if you think about the model that we were talking about in the TLC trial, okay? So in the TLC trial, you saw that we were using a treatment indicator. So we had treatment, which is either equal to active or placebo. And then we thought about time as our other covariate, right? And so we'll say that this is going to be, say, TJ. And this is just going to be an indicator variable, or actually a set of 3 indicator variables, right? And so TJ is either going to equal 1, 2, 4, or 6. And you can think about using 3 dummy variables to capture this, right? And so if we just think for a second about the main effects model here, right? We could say that the expected value of the lead for each individual, given the treatment for this individual and the time, is going to be equal to, we could have our intercept here. We'll have a treatment indicator, so that's indicator, say that the treatment is equal to the active treatment. And then we're going to have 3 additional parameters for the time indicators. So that's going to be an indicator that Tj equals 2, say, plus a factor for an indicator that Tj equals 4, plus a factor, so beta 4 now, an indicator that Tj equals 6. Okay, and so now here what we can see is that if you pose any specific individual, right? So any specific individual is going to have a treatment of either A or P, and then their observation is either going to be at times 1, 2, 4, or 6. And so for any combination of these individuals, we can see that it's just going to be some combination of these coefficients being summed. And so the idea is that, for instance, beta 1 here, beta 1 is going to be added whenever their patient has an active treatment. And so beta 1 is going to be interpreted as the difference between an individual who receives an active treatment as compared to the placebo treatment at the exact same point in time, right? Because if it's time 2, then we're going to have this beta 2 term added on. And so you need to keep that the same between these individuals. So I hope that, that this is making some sense. I assume that these types of regression interpretations you've done before, and this specific model right here, this TLC model, we're going to start exploring in R code in the very next lecture. And so I want to sort of end it here and then take this model into the next tutorial, or into the next lecture video, where we're going to be able to actually do interpretation once we can fill in values for all of these betas. So if this specific version isn't making a whole lot of sense, I hope it will come the next lecture, where we can start to sort of play around with the actual values of those things. As always, if anything that I've said hasn't made sense, or if you have any questions at all, please let me know, and I will see you in the next lecture video.